things that I think you can point to as proof that the humans are not smart. But my personal favorite would have to be that we had to invent the helmet. What was happening, apparently, was that we were involved in a lot of activities that were cracking our heads. We chose not to avoid doing these activities, but instead to come up with some sort of device to help us continue enjoying our head-cracking lifestyles. The helmet. Even that didn't work because not enough people were wearing them, so we had to come up with the helmet law, which is even stupider. The idea behind the helmet law is to preserve a brain whose judgment is so poor, it does not even try to stop the cracking of the head it's in.
This program is brought to you by Stanford University. Please visit us at stanford.edu.
Okay, so we were about to embark on a distant journey into a large black hole. Before we do, let me remind you of one or two facts. I just hope we have enough. Oh, I actually brought some pens. Anyway, let me just go back for a moment to the accelerated reference frame and just remind you of what the various facts about it are. Excuse me. The accelerated reference frame was a frame in which every observer is moving on a hyperbolic trajectory. As you get closer and closer to the light cone here, the trajectory has an increased acceleration, and you can see that from the fact that it has to turn the corner in a smaller amount of space. So it's not like an accelerated coordinate system in Newtonian mechanics, where everybody partakes of the same exact acceleration and all move off simultaneously, but rather the acceleration gets larger and larger as you move toward.
Is this an example of why special relativity does not apply to accelerated?
No, this is an accelerated reference frame.
But each person on the meter station will experience a different acceleration.
Yes, but that's also true in the vicinity of a black hole. That this point, or this whole line, in fact, replaces the black hole horizon. And if you're supported 10 meters or 100 meters away from the black hole horizon, you have one acceleration. Well, let's first take the Earth. If you lower down to the surface of the Earth, well, from a large distance, and not lowered down, but you're supported, of course your acceleration is larger the closer you are to the center of the Earth. So it's not that surprising. In that sense, the accelerated reference frame is not a very precise version of a gravitational field, because gravitational field varies. Here, in special relativity, we already have this property that the closest thing to a uniformly accelerated reference frame already has this fact that the gravitational strength, or the acceleration that you feel, varies from distance from this point over here. Okay, we also discussed, these are the different observers. They could be characterized by a coordinate r, which, at least along here, just represents how far they are from the origin of coordinates over here. They're characterized by an r. And they're also characterized by a hyperbolic angle. The hyperbolic angle, did I call it omega last time? What did I call it? Omega. Such that if you want the precise relationship with the original coordinates on the blackboard, to call them x and t, then to make the relationship precise, x is equal to r times the hyperbolic cosine of the hyperbolic angle omega, and t is equal to r times the hyperbolic sine of omega. Very, very much like polar coordinates, in which x and y completely different system now, but just by analogy. I don't use x and t, just x and y. We would write that a point is given by an r, and not an omega, but a theta. I use omega for hyperbolic angle, but it's a kind of angle. It doesn't go from 0 to 2 pi, sorry, it doesn't go from 0 to 2 pi, it goes from minus infinity to infinity. And it's a time-like variable. It's obviously moving more in a time direction than it is in a space direction. And it's some sort of time along these trajectories. But the analog here would just be x equals r cosine theta, ordinary cosine, not hyperbolic, and y equals r sine of theta. Okay, that's just to keep in mind the analogy. And if we work out, well, first let's write the metric in polar coordinates. The ordinary metric, the x squared plus the y squared, just becomes dr squared plus r squared d theta squared. There might be other directions sticking out of the blackboard. We would add them in. I'll do that over here. Likewise, the metric over here, or in similar spirit, the metric over here just becomes dr squared. Well, let's be careful. Signs are important. The r squared with a minus sign. This is proper time, d tau squared, and we have r squared d omega squared, which is the analog of the r squared d theta squared term here. Omega is like time, so it comes in with a plus sign here. R is like space, so it comes in with a minus sign. This is equal to dt squared minus dx squared. Now, if there happen to be, and of course there are, additional coordinates, the additional coordinates can be thought of as coming out of the blackboard. What would those additional coordinates be? Let's call them just y and z. Then we would also write minus dy squared minus dz squared, and we do the same thing here. So it's mainly r and omega, which are the new things, and they're kind of hyperbolic polar coordinates. Lines of constant omega, which mean lines of constant time in the accelerated coordinate system, look like this. This is omega equals 0, for example. We also can have negative omega. Omega equals 1, omega equals 2, omega equals 3, omega equals 4, dot, 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 dot. And omega equals infinity, the end of time from the point of view of the accelerated reference frame, is just this light cone here, which is x equals t. X equals t, of course, means x equals ct if I were to put back the speeds of light. And so this is just a motion of a light ray. Okay, that was the hyperbolic polar coordinates. We also pointed out that anybody who finds himself back here cannot send a message out to the observers who are out here. Of course, an observer out here can jump in, can just let go of whatever the accelerating mechanism is, let go and fall into here, in which case he can make contact. But if he stays outside, which means if he stays on these hyperbolic trajectories, but in particular does not cross this line, then let's give them names. This is Alice over here. Alice, who falls through the horizon, and Bob, well, Bob over here, who continues to accelerate. After a point, Bob cannot see Alice anymore. No, that's not quite true. Bob looks back. Let's ask what Bob sees. What does see mean? See means to look with light. Bob can see everything backward along his own trajectory, can see everything backward along light-like directions, and it takes an infinite amount of Bob's time, omega goes to infinity, before he's in a position to actually see Alice right at that light cone there. So from Bob's perspective, he sees Alice asymptotically approaching this line. We might as well call it the horizon. It would be improper to call it a black hole horizon. There's no black hole here. Sometimes it's called an acceleration horizon or a Rindler horizon. So Bob sees Alice asymptotically approach the Rindler horizon. Relative to Bob, Alice is moving faster and faster, particularly as it's Bob who's doing the moving from our point of view, but Bob is moving outward with an enormous velocity. That means that he sees Alice moving with a large velocity. What happens when you have somebody with a large velocity? They get Lorentz contracted. So Bob will see Alice getting thinner and thinner in the vertical direction, not in the horizontal direction, and as she gets sort of squeezed onto the horizon, but Alice doesn't see anything out of the ordinary. She just goes right through. All right, so that was a setup which was intended, yeah.
So will Bob see Alice's time seem to slow down?
Well, will Bob see Alice? Yes, Bob will see Alice's time slow down. What will Alice see? Yeah, she just looks back and she sees somebody scooting along an accelerated trajectory. Okay, keep in mind there's some asymmetry here when you talk about what Bob sees and what Alice sees. Let's draw the diagram again. There's some asymmetry. The question is where the asymmetry comes from, but let's see what the asymmetry is. Okay, so here's Bob, here's Alice, and for Bob to see Alice, he has to look backward along light-like directions like that. He looks backward. We all look backward. I mean, when backward in time. We can never see anything at the same moment that we're looking. We see things in the past. He looks back and he sees Alice at that point. A little bit later, he sees Alice at that point. A little bit later, he sees Alice at that point, and so forth. Alice looks at Bob. She doesn't look in this direction. She looks back this way. And she never sees Bob disappear. In fact, she just sees Bob accelerating away from her. This means she does see Bob's motions slow down because Bob is moving away from her, but if something moves away from you, they seem to slow down. But Alice, in this picture, never sees Bob disappear or anything else. She just keeps watching him as he recedes further and further into the distance along the accelerated trajectory. Yeah.
I have a little bit of confusion. I see that the Rindler space is a transform of the Minkowski.
Yeah, it's just a coordinate system. But
just a coordinate transform?
it is a coordinate transform, but now we're imagining.
Why is one accelerated? I don't see I don't see the uniform acceleration.
No, we're imagining now a collection of observers. This is not just a coordinate transformation. It is a coordinate transformation, but now we're imagining observers who are moving at a fixed r. So imagining a collection of observers, each one of which is at a fixed r. That means they're accelerating off, and we're asking what they see.
Okay, so that's,
Yeah, it is a coordinate transformation, but at the same time, we're imagining that there are people located at fixed values of the spatial coordinate, r.
And fixed r means uniform acceleration.
Fixed r means uniform acceleration. Yeah.
The d omega squared is not quite proper time.
No, it's not proper time.
It's d omega squared over
Actually,
r squared. That's the proper time.
Sorry, again?
It's d omega squared over r. D
d omega squared is not, let's say r equals fixed r, right? fixed r. ds, what did I write here? d tau along one of these trajectories, dr is 0, dx and dy is 0, so along one of the trajectories, d tau is just equal to r d omega.
R is fixed.
And r is fixed. But the rate of proper time relative to the rate of omega differs from r to r, from one r to another. Okay? So if you had exactly the same kind of clock over here as over here as over here as over here, namely clocks which tick off proper time, they would not be ticking off omega. If you want clocks which tick off omega, then those clocks have to have different rates of reading off proper time. Okay? But that's just a question of coordinates. You can imagine clocks which are built to tick off omega. You'd have to have them built differently at each point here, but so let it be. For example, the proper time between here and here is longer than the proper time between here and here. Okay? So if we wanted clocks which read off omega, they would have to run at a different rate, each one run at a different rate. Yeah.
Suppose you had an observer who was going along one of those paths, one of those trajectories, only their real x component would be displaced. And
The real, sorry, yes.
Okay. And
Don't use the word real.
well, I don't know how to put
The
that.
x coordinate.
The x coordinate, but it's not. It doesn't change as r. I'm just trying to put him at a different point in space, but with the same trajectory. In other words,
Oh, you want to put another trajectory, but at a different point of space, yes.
but which happens to have the same shape
Yes,
rather than the
right. Same acceleration.
So you have.
Yeah, okay, good.
Now, I have heard someone argue that they have different gravitational potential because of the fact that one has the displaced r value.
Remember, the gravitational potential is not an invariant thing. You can add a constant to the gravitational potential. It doesn't change anything. You could ask whether they feel different force on the bottoms of their feet. They don't. They feel exactly the same force on the bottoms of their feet. If they're being supported by...
So they don't see each other moving one direction or another?
No. They don't stay the same distance apart from each other in their own frames of reference. Since they're parallel trajectories, let's draw them. They correspond to shifting the origin by drawing the same curve. Okay. Now, in the original coordinates, this distance is equal to this distance, is equal to this distance, is equal to this distance. Just by, all we've done is translated the hyperbola. But in their own reckoning, they don't measure distance along here. Well, at this point, he does measure it. But here...
If all of these observers are maintaining constant relative distance to one another,
each in their own frame of reference sees the one ahead of him always being the same distance away.
Right.
Not true here because of Lorentz contraction. Right. So you could call this an accelerated coordinate system in which you just displaced each one by the same amount. But it would have the property that an observer moving along here would see the guy in front of him receding away and not staying the same distance.
Wouldn't that
Yeah, receding or...
opposite direction as well?
What's that?
Wouldn't the other observer also see the other, isn't it just...
Well, you got to figure it out. I'm not sure what each one sees, but whatever they see, the distance that this person over here sees to him, see is perhaps the wrong word. The distance that would be measured by a measuring rod along here would not be the same as the distance along a measuring rod along here, where this line here was chosen to be the space-like surface for a moving observer over here. Would not be the same. So I believe he would see him recede, but it's something we got to figure out. Right. The properties of what each one sees would depend on time in particular, so it wouldn't be a static description from the point of view of the accelerated reference frame. Okay, so that's good. Now let me write down, I think I did write down the Schwarzschild black hole metric last time, did I not? And the main thing I want to do today is to show you the connection between this and the Schwarzschild metric. Once you know that connection between that picture and the Schwarzschild, then there are many, many questions that you can answer simply by thinking of the corresponding question here. Okay, so let's write down the Schwarzschild metric, which looks entirely different. Here it is, the tau squared equals 1 minus 2m over r. I'm setting the speed of light as usual equal to 1. G, thank you. dt squared minus 1 divided by 1 minus 2mg over r dr squared plus r squared, not plus, minus r squared times the metric of a two-dimensional unit sphere. Why? This is what we're using basically is spherical polar coordinates. Ordinary spherical polar coordinates just wouldn't have these mg's here. It would be dt squared minus dr squared minus r squared times, I think I called it last time, the omega squared. And the omega squared is d theta squared, or is it d phi squared? D phi squared, I guess, plus either cosine or sine, depending on where you measure the angle from, sine phi squared, d theta squared, where theta and phi, just looking around you, and there's a polar angle and an azimuthal angle. That is the metric of the Schwarzschild black hole. That's all there is to it. And analyzing this, taking apart and understanding it will teach you about as much about black holes as, well, it'll teach you a lot about black holes. Okay, incidentally, just to remind you, this is also the metric of the Earth's gravitational field, but only out beyond the surface of the Earth. In other words, this is the solution, the general solution of the problem of a spherically symmetric distribution of mass outside of the place where that mass is. In other words, for r larger than the boundaries of the chunk of material. As we take the object smaller and smaller and smaller, eventually it tends to be this everywheres. But of course, there are some problems in this metric, some singularities. And there are two kinds of singularities in this metric. One of them is a really nasty singularity, where if you encountered it, you would not be very comfortable. The other is a coordinate artifact. In other words, a funniness of coordinates. Okay, the horizon is the place where 1 minus 2mg over r becomes equal to 0. 2mg equals r, that's the horizon. And why do I say something singular is happening? Well, first of all, there's something happening to the dt squared. Notice that if you're sitting right at r equals 2mg, then the proper time and the ordinary Schwarzschild time, this is called Schwarzschild time, have an infinite ratio of the rate at which they run. any amount of ordinary time corresponds to 0 proper time. So that's a little bit funny. But it really, we've already seen it. We see it right here, d tau squared at r equals 0, which is right at this point over here. This is a different r, incidentally. I think we are going to run into trouble if I continue to call this r over here the same r as over here. No, I'm going to call it rho. Rho. I'm used to calling it rho, so I'm going to call it rho, d rho squared. Rho. Of course, it's bound to happen that we'll get into these kind of conflicts of notation. I called it r originally because I wanted to compare it with ordinary polar coordinates, where we always use r. On the other hand, that r, we will see, is not quite the same as this r. It's related to it, but it's a little different. And this thing has been called r also from time immemorial. So we have to change notation. We have to give way to some other notation, either on that side or that side, and I prefer to do it over here. Okay. Now remember, though, that r and rho are related to each other. They may or may not be exactly the same thing. We'll find out. But notice over here we have this omega, which is the time from the point of view of these accelerated observers. Notice that at rho equals 0, that any amount of d omega corresponds to no amount of d tau at rho equals 0. Something like that is going on over here. At 2mg equals r, arbitrarily large amounts of dt correspond to no proper time at all. Okay? So these are funny points. Now, there's nothing physically important going on here. It's just that we've chosen coordinates which have a particular center over here, such that, I mean, it's exactly if we went to polar coordinates, ordinary polar coordinates, it would just be the statement that at the center, any amount of angle at all, right at the center, corresponds to no circumference. Okay? As you move out, a little bit of angle corresponds to a larger and larger piece of perimeter, of distance along the perimeter. So there's this kind of stagnation point in the coordinates over here, but it's not anything physical going on. So you see, there are situations where the coordinates can do something funny, where there really is nothing going on, or at least nothing that the observer at that point would notice. Okay? We're going to try to find out, is this... Now, that's, first of all, one thing happens at 2mg equals r. The coefficient of dt squared goes to 0. That's got to do with the fact that clocks slow down as you get closer and closer to the horizon. We'll come back to it, I think. But, and that wouldn't be so bad. But this also does something bad at r equals 2mg. At r equals 2mg, this goes to 1. 1 minus 1 goes to 0. And even worse than going to 0, the coefficient of dr squared becomes infinite. Question? All right. So it looks like there's something nasty going on at r equals 2mg. Well, if not from this term over here, which is doing something fairly similar to what's going on over here, the r squared term is blowing up in our face. So from one point of view, that sounds like there's something nasty there. We'll see that there isn't. Okay. Next, at r equals 0, there's also something funny happening. At r equals 0, the coefficient of dt squared blows up. But even worse, it blows up with a negative sign. When r is equal to 0, this becomes big. 1 minus something big is negative something big. So the coefficient of dt squared blows up. with a negative sign, and the coefficient of dr squared goes to 0. Why? No, is that right? Let's see, yes, I think so. At r equals 0, what's in here becomes infinite, and therefore the coefficient of dr squared gets smaller and smaller, but also with the wrong sign. So something is happening at r equals 2mg, and in fact it's interchanging the signs of dt squared and dr squared. In other words, let's imagine that r is less than 2mg. Then this is negative, and this one is positive. Okay. This term has negative, this one has been interchange of what was space-like with what was time-like. Now, does that mean that space has become time and time has become space? No, it just means that the coordinates are doing something funny, and we'll come back to what it is. All right, let me take apart this metric a little more. Instead of working with rho, I want to invent another variable. I don't know what to call it. I've run out of radial variables. I hate to introduce another coordinate. Okay, I'm going to do it. I have to. I have no choice. I'm going to take rho squared and give it a new name. Okay, let's see. Yeah. Give me a name for rho squared.
Capital R.
Capital R. Okay, rho squared equals capital R. Then we have, of course, that this is equal to r d omega squared. That goes to 0 when r goes to 0. That's not surprising. So did rho squared d omega squared. But how about this d rho squared? What is that? Let's calculate that. Let's calculate the relationship between d rho and dr. What is dr, d capital R? D capital R is equal to twice rho d rho, right? Okay. Let's divide that and notice that d rho is dr over twice rho. Now let's put in d rho squared. D rho squared is minus dr squared divided by, in this case, it happens that there's a 4 there. The 4 is not the interesting thing. We could get rid of the 4 by a trick. But with rho squared in the denominator, right? Everybody see what I did? I just wrote d rho is equal to dr divided by 2 rho, and I stuck it into there. What is rho squared? Rho squared is r. Forgetting about the 4 we could actually soak up into a change of units of r. I simply actually chose the wrong definition. I should have put a 1/2 in here or something. Would have gotten rid of this 4. But there it is. Let's look at this metric. This now has the omega squared term goes to 0, just like this one does, at r equals 0. At r equals 0, it has the same property as this, namely something goes to 0. On the other hand, look what's happening over here. Also at r equals 0, the coefficient of the dr squared term is getting infinite. What was in the numerator here appears in the denominator here. What's in the numerator here appears in the denominator over here. There's nothing pathological in the space-time over here. I've just used some pathological coordinates which have the property that the metric has, in terms of the time component, it has something which goes to 0 at r equals 0, and in terms of the space component, it has something which goes to infinity. There's something, shall I slow down here? Okay, everybody with me? All right. So we see in itself, there's nothing pathological in the space just because a coefficient here goes to 0 and a coefficient here goes to infinity in the same way. As I said, The relative 4, which appears here, is not an important issue. Now, there's something else. If we looked at this metric here, and we thought of r as our coordinate, notice what happens when r goes from positive to negative. When r goes from positive to negative, this term becomes negative, and this term becomes positive. Whatever r less than 0 means, if it means anything at all, it has this interchange of space and time, just as this does. Just as this does. So the question is, can we understand what r less than 0? R is rho squared. How can rho squared be less than 0? Okay. The point is, rho squared less than 0 is up in here. Let's see if we can understand why that is. Each one of these hyperboloids, or hyperbolas, corresponds to, let's see what it is. It's x squared minus t squared equals rho squared. Each one of these hyperbolas corresponds to a different value of rho. And precisely the same way as for a circle, we would have x squared plus y squared equals rho squared. Here we have x squared minus t squared equals rho squared, which happens to be what I called r. Also known as rho squared. What happened when r got negative? Look at this. What happens when r gets negative? Let's suppose r goes from +1 to -1. So x squared minus t squared equals 1. That's a hyperbola like this. What happens when it gets to be -1? Then it becomes x squared minus t squared equals -1, or t squared minus x squared equals 1. That's another hyperbola. Where is that hyperbola?
90 degrees off.
Yeah, that's a hyperbola up here. Let's look at it right at this point over here. At that point over here, t is equal to 1, x is equal to 0, and t squared minus x squared is equal to 1. So it's not that anything crazy has happened over here, that space has become time and time has become space or anything like that. It's just that the coordinate that we're using has a funny property. Let's think about what r equals 0. Let's see, r equals 0 means. On this side over, not r equals 0, sorry. Not r equals 0. Yeah, omega equals 0. Omega equals 0. Omega equals 0 is this line over here. Okay. That's what it is when r is bigger than, when r is positive. When r is negative, it just becomes this line here. So it's crazy coordinates in which what we're calling time makes a right-angled turn over here. All right. Here's omega equals 1. Omega equals 1 looks like that, and then when it gets to this point, it makes a turn and it goes over here. So the main point here is that coordinates, if they're chosen in some funny way, can make it look like something very dramatic is happening at a point, when in fact there's nothing dramatic happening over there. It's just that we've chosen coordinates that do funny things. Okay, how do we actually go from, how do we actually go from this metric? Is there some approximation in which it is just this metric over here? Can we see some approximation in which these two things are the same? And if we can, we will have learned something important about the black hole. We would have found an approximation, certain situations, where the black hole is really approximately flat space-time.
Would that be how far you're away from the horizon?
Yeah. Yes, that's right. Right. Okay. So let's take this metric and fiddle with it a little bit. We're going to be interested in it very near the horizon. We're going to try to analyze it very near the horizon. Near r equals 2mg. Let's rewrite this. This is r minus 2mg over r times dt squared minus the r squared divided by, or multiplied by r divided by r minus 2mg. I've done nothing. Forget the r squared. No, we'll do something with the r squared, the omega squared in a minute. All I've done was write 1 minus 2mg over r as r minus 2mg over r. That's nothing at all. And now I'm interested in the vicinity of the horizon, r very close to 2mg. Well, I can't set r equals to 2mg over here. That's too extreme. I do want to keep track of the fact that we're not right at the horizon. But on the other hand, the r over here, there I can set it equal to 2mg near the horizon. This doesn't, as I move near the horizon, a little closer, a little further, r doesn't change very much. Let's suppose r is a kilometer, and I move in and out, capital R Schwarzschild. Supposing the Schwarzschild radius, 2mg, is a kilometer, and I move in and out by a millimeter. What happens to r? Well, it changes from a kilometer to a kilometer plus a millimeter, a negligible change in r. All right, so I might as well over here just write that r is equal to 2mg, and that's a good approximation. I don't want to do it in the numerator, because although r doesn't change very much, percentage-wise, r minus 2mg does change a lot when I go from r, from near the horizon. It can actually change sign. So I don't want to muddle with this, but in the denominator, not much happens when I change r a little bit near the horizon. Likewise over here, 2mg. That's a good approximation to the metric very near the horizon. Notice it still has the property that it goes to 0 when r goes to 2mg, and this one goes to 0 in the denominator when r goes to 2mg. And I've made a small approximation near the horizon. Now let's see what's going on over here. Minus r squared. Again, what we have is, yeah, we move in a little bit closer or a little bit further from the horizon. R squared doesn't change very much. It changes from a kilometer squared to a kilometer plus a millimeter squared. It doesn't change much. And so very, very close to the horizon, we might as well call this also 2mg squared d omega squared. Okay. We'll come back to this over here. This is what we're doing. Let me tell you what we're doing. Here's the horizon of the black hole, r equals 2mg. We're interested in the neighborhood of a point near the horizon. I'm interested in what somebody sees who moves in and out. Well, if they move in, they don't move out again. But if they're moving a little bit near the vicinity of this horizon, and they simply want to blow this up. They want to blow it up, look at it under a microscope, and see what the horizon looks like. Okay? So, apart from the pieces here where we have to keep the difference between r and 2mg, we've simply set r equal to 2mg. Now, what's going on over here? What is d omega squared if I look only in the immediate vicinity of this point? If I look only in the immediate vicinity of this point, it's like looking at the immediate vicinity of a point on a sphere. A point on a sphere, in the immediate vicinity of a point on a big sphere, just looks like a flat plane, right? This, whatever it is, it's a sphere of radius 2mg. That's what it is. It's a sphere of radius 2mg as I move around on here. But a sphere of radius 2mg, it doesn't matter how big the sphere is, as long as it's big enough, when I move around on it, all I see is a flat plane. So I can actually replace this by a flat plane. It's just a tangent plane to the sphere, just like we replaced the tangent plane to the Earth by flat space, the flat space approximation. It's not good for the entire horizon, but it's good for the neighborhood of the horizon. So actually we can replace this by dy squared plus dz squared. The two coordinates, this coordinate here, we call whatever, r. The other two coordinates I'm calling y and z, and this can just be called dy squared plus dz squared. Why? Because in the immediate vicinity of a point, it can be approximated by a plane. If we approximate it by a plane, it's just dy squared plus dz squared. So now we're getting there. We have the metric right at that point, in the immediate vicinity of that point. Here it is, r minus 2mg over 2mg, the r squared, 2mg over r minus 2mg, and the other pieces of it. Very simple, almost trivial. Just dx squared plus dy squared. Dx squared minus dz squared plus dy squared. Now, I just want to emphasize, this is not the exact metric of the black hole. It is the metric of a piece of space very close to a particular point. What we're trying to find out is what is actually going on in a small neighborhood of that horizon. Is there something nasty and vicious because r is going to 2mg? Or is it more like this over here, where there was in fact nothing nasty or vicious going on? It was just a flat region of flat space, flat space-time. Okay, so this has vague similarities with this. Something in the numerator, the same thing in the denominator. A factor of 4, which I wasn't very careful to, I could have defined, as I said, I could have defined things in a way to get rid of it. I didn't, so there it is. Okay, let's change coordinates again. Now, this whole game is a game of changing coordinates until you find coordinates where you recognize what's going on, where you recognize with some simplicity what's going on. I don't want to change to this capital R coordinate. This capital R coordinate was just a contrivance to show you that there are situations where a numerator of one thing can become will be the denominator of the other. When this goes to 0, this one goes to infinity. That was just a contrivance to make it look as much as possible like this. But I'm really more interested in the original polar coordinates here. Here's the original polar coordinates. And my claim is that by a smart change of variables, I can make this metric over here, these two pieces of it, look exactly the same as this, close to the horizon. All right? How can we do that? Well, the trick is to realize what rho is. Rho is the proper distance from this point over here. Spatial distance. It's the proper distance. How do I know it's the proper distance? D tau for move out along here. D omega is equal to 0 if I move horizontally. And d tau is just equal to minus, d tau squared is minus d rho squared. That's definition of proper distance along here. Okay. Let's see if we can find the proper distance from the horizon to an arbitrary point r. Here's an arbitrary point r, and then use that to replace the coordinate r. The proper distance from the horizon to that point, I want to use that as a new variable. I'll call it rho again. How do we find the proper distance from this point over here, which is r equals 2mg, to an arbitrary point r. Well, anybody have a suggestion?
Plug in 0 for the other coordinates?
Yeah, we'll plug in 0 for the other coordinates, but then we have to do a little bit of work. Yeah, we're going to move out, straight out, without changing time, without changing x, or without changing z and y, and see how much proper distance there is between here and here. The proper distance is determined by this term in the metric. If we move out without changing time and without changing dz and dy, then the proper distance that we move out, let's call it ds. ds squared is the same as d tau squared except with a minus sign. The proper distance, ds squared, is just equal to dr squared times 2mg over r minus 2mg. Okay, we take the square root of that. Now, how do we find the distance from this point to that point? We have to do an integral. The distance is the integral of this. Okay? This is the differential distance when you change r by a little bit. If we actually want the distance from r equals 2mg to an arbitrary point, we have to integrate. So let's call that integral rho. It's the proper distance to an arbitrary point, and it's the integral d rho square root of 2mg, that's a constant, that comes out, divided by r minus 2mg square root. Here we are. This is the proper distance. Where do we integrate from? We integrate, sorry, this is dr. dr. We integrate from r equals 2mg to r. I'm going to stop for questions at this point because this is quite critical to understanding what's going on. But
What's that upper limit again?
that's just the point r. Okay, let's call this r prime, the integration variable. Right. Right. And we integrate from r equals 2mg to the moving point, or to the arbitrary point r. Right. R outside the horizon, to be specific. Okay, can anybody do it? Well, let's first of all just take the 2mg outside the integral. That's easy. That part is easy. Yes, there's a 2mg, of course. So we take out the 2mg in the numerator here, and we have an integral to do. It's a square root integral. It's a simple square root integral. It's 1 over square root of something. And what's the integral of 1 over square root? Yeah, who can do 1 over square root? X to the minus 1/2 integrated. What is that? It's x to the 3/2, sorry, x to the plus 1/2, and then a 2. Yeah, 2, right? The integral of x to the minus 1/2 is twice x to the 1/2. How do I prove that? I differentiate this. I get x to the minus 1/2, and 1/2 times 2 is 1. Good. Okay. So here we are. Rho, the distance between the horizon and a point r, is given by,
We lost the square root of the 2mg.
did I lose a, I think I did. You're absolutely right. Right, we had to take the square root of this whole thing. Good, thank you. There's a square root of 2mg, that was in the numerator, and then a square root of r prime minus 2mg in the denominator. The square root came from taking the square root of ds squared, dr square root, square root. Okay, so what do we have? We have then that rho is equal to twice, that's the 2 from here, then there's the square root of 2mg, that's from here, and then the square root in the numerator. Square root of r minus 2mg, where I've plugged in the endpoint into the integral. That's rho. Again, what is it? It's the proper distance from the horizon to an arbitrary point at distance r. It's also a change of variables. It's also a change of variables where I have now imagined a change of variables which I substitute for the variable r, the Schwarzschild coordinate r, I substitute the coordinate rho. Notice there's a square root. Let's see, did we have, if you remember, r was equal to rho squared. Again, there was a variable over here which was related to a variable over here by a square root. Rho is equal to the square root of r. Here we have rho related to the square root of r minus 2mg. So they do look similar. Okay, let's rewrite the metric. Let's rewrite the metric. It's a bit of a nuisance. It's not very hard. I'm taking you through all the steps. I could just write down the answer, but I want to take you through the steps. Here we are. No coordinate. Coordinate transformation to proper distance, which is just equal to square root of 8mg. I got the 8 by bringing the 2 inside, times square root of r minus 2mg. That's the proper distance from the horizon. And all we have to do now to rewrite the metric is well, we have to figure out what it is. First of all, rho over 8mg is r minus 2mg, is square root of r minus 2mg. So let's square it. Sorry, square root, right? That's rho divided by square root of 8mg is equal to the square root of what's on this side. Let's square it. Rho squared divided by 8mg is equal to r minus 2mg. Well, that's convenient because we have r minus 2mg all over the place in this metric here. So it's convenient that we know what r minus 2mg is. Let's now rewrite the metric. First of all, there's this term. I realize that this is a tedious thing to sit through. You don't need to sit through it. You can do it yourself, but let's do it together. All right, here we are, r minus 2mg over 2mg. Well, here it is. R minus 2mg is rho squared over 8mg. Then I believe there's another 2mg down squares. That makes that 16 m squared g squared, right? Times what? Times dt squared, right? Now what about this monstrosity over here? Anybody? There's a quick answer to this, a really quick answer to it. What it is in terms of rho. Anybody? Yeah, but then we'd have to also convert d rho, dr to d rho. All right. What was the definition of rho? No, the definition was the proper distance from the horizon. If rho is the proper distance from the horizon, then this is just d rho squared. It is the proper distance from the horizon. The way we got rho was basically writing that d rho squared is dr squared over 2mg is just equal to this thing here. So we don't have any work to do to figure out the rho part of the metric. It is just d rho squared. It is the proper distance, minus, minus, minus. Minus good old dx, dz squared, and dy squared, which go along for the ride. We're almost there. What are we comparing this with? Let's go back. Where's my Rindler metric? My polar coordinate metric. My polar coordinate metric was rho squared d omega squared minus d rho squared. And if there were other coordinates coming out of the blackboard, if there were other coordinates coming out of the blackboard, then we would put them in by hand, minus dz squared minus dy squared. Is this the same as this? Not quite. What's the difference? 16 mg squared. Okay? But now there's a simple thing we can do. We can just make a change, another change of variables, namely, let d omega equal, or just let omega equal t over 4mg. Omega squared is, well, let's just do d omega. D omega is equal to 1 over 4mg dt. And guess what? D omega squared is just dt squared over 16 m squared g squared. So I just look at this and I say, oh my goodness, this is nothing but dt over 4mg squared. And so all I have to do is change variables from t to omega. And this becomes rho squared d omega squared, blah, 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 the same thing as this here. Okay, so let's just go through what I did again without actually doing it. I changed, well, the first thing I did was I approximated near the horizon. It's called the near horizon approximation. And it's not just the near horizon, it's near a specific point on the horizon. We substituted for 1 minus 2mg over r minus 2mg over r, and then said r is approximately equal to 2mg. So that just gave us a simple expression over here. Same thing upside down over here. And then this metric on the sphere was approximated by the tangent space, which just means it's the same operation as when I do on the surface of the Earth. I use x and y for a small patch. On a farmer's field, he doesn't need to keep track of the curvature of the Earth. He just needs x and y, or north and east, or whatever, and uses the flat space metric. Okay, that was the first step. Simplify this way. Next step was to compute the proper distance that corresponds, in other words, really simply stated, it was just setting dr squared over 2mg times r just equal to d rho squared, and figure out what rho is. Let's write it that way. Let's just think of it that way. Dr square root of 2mg over r minus 2mg equals d rho. Definition of d rho. I took the square root of this, square root of this, square root of this. And then I integrated to find out that rho was nothing but, where is it? Here it is. That gave me a new coordinate rho, which simplified this term. The main point was it simplified this term. Why did it simplify it? Well, dr times this piece of stuff over here is just equal to d rho. So this just becomes d rho squared. This, on the other hand, was also not too complicated. It just turned out to be rho squared divided by 16 m squared g squared.
Could you justify again, please, why d rho is dr?
Why what?
D rho equals dr.
Who said d rho equals dr? Yeah.
D rho squared equals dr squared.
I didn't say that. d rho squared is equal to dr squared times 2mg over r minus 2mg.
Yes, but over the other side here, you replace it with d rho squared.
Say it again?
Second term, right, at the top of the right hand. D rho squared, right there. Where you touch the d rho squared.
Yeah, but you didn't replace dr squared with that.
No, I didn't. I replaced dr squared divided by this. Okay, look. Here we are. Let's go back one more step. Do it once more. Here we have this dr squared over 1 minus 2mg. Well, 2mg over r minus 2mg, okay? Whoever asked the question, are you happy with that? I didn't do anything, I just rewrote it. I'm setting that equal to d rho squared. Now you can't ask me why afterwards why d rho squared is equal to this, it just is. Okay? Definition of d rho squared. I take the square root of both sides and I integrate to find out that rho is equal to this. Now there's no question that this thing over here is equal to just d rho squared. It's the way it was defined. It was just a trick to redefine a coordinate to simplify this thing over here. That's all. You can always do it. You can always make a change of variables to change from dr to d rho, where by definition dr times this square root here is equal to d rho. Okay, so by the time we're finished, we get back to here. Well, that's pretty interesting. It tells us, what does it tell us? It tells us that the geometry, the near horizon geometry, very near this point, is really no different than the geometry of flat space-time in polar coordinates. You can't tell the difference very, very close to the horizon of a black hole. You can't tell the difference between flat space and the black hole, number one. Number two, this rho variable, which was proper distance from the horizon, and which enters into the metric in this form over here, is obviously close to the horizon, the same variable as the accelerated coordinate system uses to distinguish one observer from the other. Just the ray, or I don't know what to call it, the variable from one coordinate to another. So the horizon of the black hole, okay, the horizon of the black hole, and different observers stationed at different distances are just like the observers stationed at different distances in the accelerated reference frame. Why accelerated? Because gravity and acceleration are the same thing. If I station somebody over here near the horizon of the black hole, but stationary, I mean hold them there. Hold them there by a rope around their neck. They're going to be, if they're going to feel like they're being pulled, they're going to feel like they're being accelerated in that direction. The further out we are, the less the acceleration, the less stretching of the neck. Same thing here. To keep somebody on one of these accelerated coordinate systems, you might imagine pulling them along by a rope around their neck. The closer they are to the horizon here, the harder you have to pull them. So it's exactly the same geometry. The near horizon geometry is the accelerated coordinate system geometry. Of course, all it is good old flat space-time, but the coordinates in this region here are not 10 after 9. No, I keep making a mistake, right. Okay, it's time dilation near a black hole or something like that. It's going too fast. Okay, so that what does it tell us? It tells us that, as I said, repeated over and over again, the horizon of the black hole is not a singular place. Now, in particular, again, the fact that the relative sign change between here and here that makes it look like space becomes time and time becomes space, there's nothing really happening. What it corresponds to see what it corresponds to, we have to go back to that capital R coordinate, and I'll just remind you, the capital R coordinate, which was R equals rho squared, is that what it was? Yeah. The metric in terms of that was R dt squared minus, and there was a silly 1/4 that doesn't mean anything, R downstairs, the R squared. So that's very much like what's going on here. Yeah.
If you go on this side of the blackboard, the accelerated object is closer and closer to the horizon, but never gets there in infinity, not in a finite amount of time. And same on this side of the. So how does anything ever get into a black hole? It takes an infinite amount of time.
All I can do is point you to this diagram. From somebody looking from outside, this line here is omega equals infinity, right? Omega 0, 1, 2, 3, 4, omega equals infinity out there. From the reckoning of the accelerated coordinate system, first of all, nothing passes the horizon until omega equals infinity. And furthermore, somebody watching, they can wait forever and ever. They go way out here. That's a long time in the future, according to this fellow here. He looks back and he still doesn't see anything having crossed the horizon. Here it is. Here's the horizon. He looks way back even after a very long time. He may be close to that horizon. He has not crossed it. He looks back and he sees poor Alice having not yet crossed the horizon. Now, exactly the same thing happens here. Exactly the same thing. And this is the picture to come to when you're all right, now there is a difference. There is a difference. The difference is far from the horizon. Far from the horizon, the metrics are quite different. Close to the horizon, it looks like good old flat space, but flat space in these strange accelerated coordinates. And strange, I mean they have a singularity over here. Time is this hyperbolic angle, but far away, when R is very large, this is small, 2mg over R is negligible, 2mg over R is negligible, and it just looks again like flat space, but flat space in which time is time and space R, with ordinary coordinates R and T. So there's a transition from very close to the horizon, where it looks like flat space in polar coordinates, to very far away, where it just looks like flat space in ordinary coordinates. Far away, you would not be tempted to call T a hyperbolic angle. But close in to the horizon, T, or at least T over 4mg, where is it? T over 4mg, omega was T over 4mg. Yes, T over 4mg, close in, becomes a hyperbolic angle. So there's a characteristic difference in these coordinates close to the horizon and far from the horizon. I can give you well, I won't give you another analogy for it. It'll just get confusing.
Any observer, no matter where they are, has something infalls towards the event horizon. Mm-hmm. Doesn't matter how far away or close it is, because it's continuous. No one will ever see it actually get to the event horizon.
Nobody who stays outside the black hole.
Yeah, no matter how close you get.
That's right.
So unless you're at the event horizon or inside the event horizon, no one will ever see anything enter the black hole. So how can a black hole ever get larger? Because nothing ever goes into it.
It gets larger by depositing its energy very, very close to the horizon and causing the horizon to grow a little bit. It's questionable whether you should distinguish the stuff which is very close to the horizon from the horizon itself. The horizon grows. not because anything goes into the black hole.
Close enough that.
It just merges with the horizon.
And what is that distance? Can it be articulated?
Yeah, it's the Planck distance.
Does that relate to this, or doesn't?
No. At some point, as you watch, imagine what happens as you watch something fall through the horizon. That something is sending out signals, right? It's sending out radio signals, or sending out, let's say it's sending out light. Let's see if we can see what happens, what's observed from the outside. We can do it by drawings, or we can do it by equations. I prefer to do it by drawings.
Why did you reject radio signals?
What's that?
Why did you give up on radio signals?
Oh, because radio signals, I wanted to start with something shorter wavelength and then get to longer and longer wavelength. Radio, there's nothing longer than, I don't know any name for a thing longer than a radio signal. So if I want to start with something short wavelength, I'll start with, what did I say, optical light? Optical light, what comes after optical light? Infrared, after infrared is microwaves, after microwaves, and so forth. I wanted to have a range that I could talk about. Okay, so let's so here's Alice. Alice is going in, and she's sending out, in her own reference frame, she's got a little oscillating dipole, which is sending out light, a little atomic dipole, which is oscillating, and here are the oscillations. One oscillation per unit of proper time in some units, which is appropriate to the emission of light. So a wave crest from here, a trough from here, a crest from here, a trough from here, and so forth. And that's Alice. Here's Bob. And Alice is sending out, I wish I had another color. I don't have another, let me see if I do have another color. No. And I'm not going to leave these psychologists my pins. Okay, so let's see what Bob sees. Bob sees a wave. The first wave hit him over here. The second wave hits him over here. The third wave hits him over here. The 25th wave hits him over here. How much proper time is there between the waves as they hit Bob? That gets drawn out longer and longer. One way to see it is just to say that Bob is receding and therefore a Doppler shift. From this point of view, there's no real difference between Doppler shift and gravitational redshift. As Alice gets closer and closer to the horizon here, she sends out waves, and the last wave that she sends out over here gets to Bob at a very, very late stretched out time. If the waves actually have finite frequency, then there's going to be basically a last wave that she sends. This means that Bob sees Alice more and more redshifted. She's sending out light signals, but Bob sees after a short amount of time, or a certain amount of time, he's receding away, and he sees infrared, then he sees microwave, then he sees radio waves of a meter, and then he sees radio waves of a kilometer, and then he sees radio waves of 1,000,000 kilometers. And radio waves with 1,000,000 kilometers don't have very much energy. They're sending out, one photon or some number of photons per unit time Alice is sending out. Bob is receiving those photons slower and slower, and they're longer and longer wavelengths. So the energy that he's receiving is getting lower and lower. What he sees is Alice's dipole slowing down. In fact, everything about Alice, because he sees it through light, he sees slowing down. And you don't need black holes to see it. You just see it from this picture here. That Bob sees Alice slowing down and slowing down and slowing down. And finally, she sends out her last wave. Okay. Why is it the last wave? Well, if she had higher frequencies, she could fit some more in there. And yet higher frequencies, she could fit even more in there. But with any finite frequency oscillator to send out the radiation, there's going to be a last wave that she sends out, and then Bob doesn't see her anymore. She's gone as far as Bob is concerned. What does happen is the remnant of Alice is merged with the horizon and in fact makes the black hole a little bit bigger. Now, to see that, we would have to solve Einstein's equations with infalling material and so forth. That's a little bit hard, but it's easy, yeah.
So the longest wavelength that she puts out of the size of a black hole, or did she put out something bigger?
That's about, no, that's right. The longest wavelength you can put out is about the size of a black hole.
Does Alice see Bob slowing down?
Okay, so does Alice see Bob? What Alice sees is Bob receding away and moving closer and closer to the speed of light. Now, when something goes past you with the speed of light, yes, it is slowed down. It's slowed down by Lorentz contraction. So yes, Alice watching Bob, well, yes, okay. Alice watching Bob sees Bob recede away and therefore, yes, slow down. There's a problem for Alice though. This is the near horizon geometry, and we haven't talked about what happens at r equals 0. Something really bad happens at r equals 0. That is not a coordinate singularity. If we were to calculate the curvature, in particular, let's say the curvature scalar, well, no, not the curvature scalar, some measure of the curvature of this geometry, we would find there's nothing radical happening at the horizon, but at r equals 0. Remember, r equals 0 was the place where, let's go back to Newton. What happens at r equals 0? Gravity becomes infinite. Tidal forces become infinite. Right. If we calculate the tidal forces associated with this thing here, we would find they become infinite at r equals 0. Okay, so r equals 0 is a real, genuine singularity, a place where curvature becomes infinite. It's a place where tidal forces become infinite. It is not a place which is anything like flat space. But the question is, where is it on this diagram? Let's redraw the diagram and try to figure out where.
You said that that's only, this is not a case when the mass is inside of.
What's that? Tell me what?
Or the mass is inside of where you are. Where the mass is inside of where you are.
Yeah, but now we've had a complete gravitational collapse and things collapse to a point. Yeah. It's collapsed to a point.
This mathematics doesn't allow anything to move to a black hole.
No, don't tell that to Alice.
But Alice isn't here.
Right.
Alice?
Yeah, no, she went right behind the black hole.
I have a question. Alice has some friends. They're having a conversation. Doesn't matter which direction they are relative to each other, they just have a conversation.
Well, Bob, they're both falling freely?
Alice and her friends are all falling freely through the
Yeah, they just talk to each other just as if nothing was happening until they get near the singularity.
Well,
Yeah.
if one friend is ahead of the other, then they can't talk. Then
Oh, yes, they
one
can.
can be behind the horizon quicker than the other. Right?
What's that? Say it again.
If one is a little ahead of the other, then they can't communicate when one gets behind the horizon, the other's still behind.
Well, okay, so let's analyze that. Here they are, they're both falling, okay? They're communicating back and forth freely, nothing funny happening. Now it is true that once Alice, here's Alice and here's Shirley. Alice is ahead of Shirley, she's fallen in first, here she is. Just as she gets near the horizon, she sends a signal out to Shirley. Shirley gets the signal. Once she passes the horizon, she cannot get a signal to the Shirley who is before the horizon. There's no way she can get a signal from here to here, but she can get a signal from here to here. Even if there was no black hole, she couldn't have gotten a signal from here to here. That would have exceeded the speed of light. So Alice sends Shirley signals. Shirley sends Alice signals. Nothing funny about them. Now, if Shirley would have decided not to go into the black hole at the last minute, here she is, and then she decides not to go into the black hole, not to cross the horizon, but to get onto one of these accelerated trajectories. Maybe she was connected to the space station by a cable, and the cable only let her go down so far and then got pulled taut. She's supported away from the horizon. Then Alice can see Shirley, but Shirley cannot see Alice behind the horizon. There's no way she can see behind the horizon. So if Shirley freely falls, her relationship to Alice is not unusual. Back and forth, they can communicate. If Shirley, at the last minute, decides not to fall through the horizon, then indeed Alice falls out of her experience. Yeah?
So type of ionization doesn't occur at the horizon?
What kind of thing?
Atoms don't ionize at the horizon?
Well, now we're getting into quantum mechanics, which we're not going to do this quarter. But do atoms ionize near the horizon? That depends on who's watching them.
If an object is moving along these dy or dz, which means kind of moving right on that surface, would it continue moving there? Those get kind of orbit.
No, it'll fall into the horizon.
But if space is flat there, it should kind of keep being flat.
Yeah, the problem is that these trajectories that move along here are going to be space-like. And why is that? Supposing we have a trajectory very close to the horizon, okay? That's moving with a dx, or sorry, a dy or a dz, okay? So let's see, so that means dy or dz is not equal to 0, right? But we're extremely close to the horizon, let's say practically at the horizon. Then this term is 0, and this term is 0. Oh, sorry, well, this term is 0 because dr is equal to 0. We're not moving in and out, we're only moving along the horizon, right? Okay? So this one's not there because dr is equal to 0 along that motion. And this one's 0 because the coefficient of dt is equal to 0.
Second one's 0 over 0.
We're slightly away from the horizon, just outside, okay? But the main thing is dr is exactly equal to 0. We're skirting the horizon at a fixed r. That was the question. If you skirt the horizon at a fixed r, that means this is exactly 0. All right, and r minus 2mg is just a small number. On the other hand, this is not 0, but it's very, very small. In particular, the coefficient here is so small that if we get close enough, this will eventually get smaller than dz. So if we make a little excursion along dz here by a given distance, no matter how long we take to do it, if we're close enough to the horizon, this term is 0. That means the trajectory here is space-like, and it means it's exceeding the speed of light. So anything that tries to skirt along the horizon is exceeding the speed of light. And that's because time has slowed down so much, or the coefficient of the dt squared has slowed down so much that the trajectory becomes space-like. Do you understand the difference? You understand what a space-like trajectory is? Right. So skirting along the horizon is forbidden motion. It's motion faster than the speed of light. Supposing, all right, let's talk about a thing. Well, I think that'll do it. Right, so you can't skirt along the horizon like that. Let's get to the singularity now. The singularity is at r equals 0 here. Now, let's remember the connection. R equals 0, or r equals small. Let's take small values of r. For small values of r, that's where the interchange between positive and negative has taken place. Okay? For small values of r, we're in here. Small values of r don't correspond, fixed values of r don't correspond to time-like trajectories, trajectories of observers, but they correspond to space-like surfaces like this. Just to see what's going on, let's go back to this metric over here. Supposing if r is positive, then we're on the outside. If r is negative, we're on the inside. All right, so here's the inside, here's the outside. In this case, r being negative, it's different than little r being negative here. It's like r minus 2mg being negative. Big R is like r minus 2mg. All right. When big R changes sign, the hyperboloids x squared minus t squared equals r become hyperboloids like this. So fixed r outside corresponds to the motion of an accelerated observer. Inside, it corresponds to a kind of space-like surface. Another way to say it is fixed r inside the black hole is some time, not some place. It's a time and not a place, fixed r. Okay? Now, what about r equals 0? Well, r equals 0 is sort of like capital R equals negative. As I said, r minus 2mg is sort of like capital R. What does r equal something negative correspond to? It corresponds to a surface like this. So little r equals 0 is a surface like this. This is little r equals 0, like that. That's the singularity. And it's not a place so much as it is a time. Once you fall through here, notice, once you fall through here, you have no way of avoiding this singularity. The speed of light is 45-degree angles. You cannot move faster than the speed of light. When you're out here and you send a light ray in the outward direction, it might escape. If you send it in the inward direction, it might hit the singularity, will hit the singularity. If you're inside, it doesn't matter which direction you send the light ray in, you're going to hit the singularity. Yeah?
If you're free falling, there's no reason for you to use these funny coordinates.
Well, free falling just means you move in straight lines. You don't have to use any coordinates. Here's the geometry.
The whole idea that the time and x and t coordinates have switched is because of these funny coordinates.
The coordinates are funny, but the geometry, this is the geometry. This picture doesn't require, let's take the r equals 0 away. That's it, that's the geometry. That's the geometry, that's what it looks like. I don't need to put any coordinates on it. That's what it looks like. And once you're in here, you can't escape falling into the singularity here. Yeah.
The whole idea of time and space switching.
Well, I keep telling you, time and space don't interchange. It's just you've drawn coordinate axes which make a right angle turn here.
Right, so basically everything is, other than, except for tidal effects, the free-falling observer doesn't...
Nothing.
Yeah.
No.
So at a certain proper time, that's it.
At a certain proper time, you've crossed the horizon, but crossing the horizon is not in itself a dangerous event. You're doomed, but you're not dead.
You have a particular specified proper time, and then you will reach the
Right.
singularity.
Right.
You might not be going at that 45-degree angle, you're going less.
If you just fall in and you pass the horizon, you have some particular amount of time left over. Yeah, 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 that's right. The maximum amount of time that you have is basically approximately equal to the time that it takes to cross the horizon of a black hole. It's just a numerical fact. If you measure distances and time in the same units, c equals 1, then the Schwarzschild radius becomes a time. Schwarzschild radius of a star would be about a kilometer, excuse me. Light takes blah, blah, blah seconds to cross a kilometer. 1 over 3 times 10 to the 5th.
So it's the diameter
Yeah.
or
It doesn't matter. Order of magnitude. Order of magnitude. Order of magnitude, it takes about 1 transit time across the black hole, and then you're in the sun.
And then once you're there, that's you stay there.
I don't know what to say. Once you're there,
Can we say any more about that?
no. No. Everything becomes infinitely dense, infinitely distorted, infinitely, quantum mechanics becomes important. Everything is torn apart into its constituents and worse. And we're into real terra incognita. But really, you're never going to get far enough to experience that singularity. And so, yeah.
Does the singularity actually, does the infinity actually exist in real life, or is there something happen right before you get there that sort of mitigates that factor, quantum mechanics or something like that? Forbids the-
Well, nobody really knows. Nobody really knows. My own feeling is no, it's an ultimate end of things. But let's put it this way. Let's just say nobody really knows. But we know how to follow it, for example, into a region where the curvature might be, the radius of curvature might be no bigger than the radius of a proton. Easy to follow it there. Nothing, we know very, very well what physics is like down to those distances. So you would not like to be squeezed into a radius equal to the size of a proton. Actually, yeah, tidal forces would be of that magnitude that they would...
So does it seem there's no sense of impact really with a large mass?
with the horizon. There's no sense of impact with the horizon. There is something dreadful that happens at the singularity, but the singularity, as I said, is not so much a place. The singularity, if the singularity was a place, a spot over here, and you're falling in, well, you could go around it. If the singularity is the end of time, as I've drawn here, there's no way to avoid it. So there is something I should tell you about genuine black holes. You would not survive the transit across the horizon of a stellar mass black hole. The tidal forces are just too large. If you were to estimate, and this is a Newtonian calculation, if you were to take a stellar mass and compress it down to the size of compress it to the size of a black hole, which would be about 1 kilometer, well, 1 kilometer doesn't seem very small. It seems like you could pass through it safely. But the tidal forces, just the gradient of the gravitational field would, squeeze you out like toothpaste through so that would be, it would be very dramatic going through the horizon of a, on the other hand, if you were as small as a paramecium, then the gravitational gradients across your body would be negligible, and you would fall right through the horizon without any trouble. Similarly, if we took a black hole which was, I don't know, 1 billion solar masses, the horizon is so big and so flat that the tidal forces are not very strong on your body at 1 billion solar masses. It's a little bit, how shall I say, a little bit counterintuitive. You might think the bigger the mass of the black hole, the worse it is to go through the horizon of the black hole, but that's not true. The point is that the bigger the mass of the black hole, the bigger the horizon, and the less curved and the less tidal forces, the less you would be squeezed going through the horizon. So if a black hole were a billion solar masses, you would go through the horizon pretty easily. I think I once estimated, I can't remember whether, let's see, a billion solar masses, so it's a billion kilometers. How long does it take to go a billion kilometers? About an hour, right? Is that right? A billion kilometers is like the radius of the solar system. Yeah, there's about a radius of solar system, which is about a light hour. So right, so with the biggest black holes that are found at the centers of the biggest galaxies, you could probably last for half an hour or something like that after falling through the horizon. Not longer than that. That's how much time it would take light to go across it. Take a black hole of 1 trillion solar masses. There are no such things. Probably there are no such things. You would last another 1,000 times longer. So going through the horizon of a black hole for a stellar mass black hole is not as innocent as I've made it sound. But the principle is there. A sufficiently small living creature would survive going through the horizon even of a solar mass black hole. It wouldn't last very long. Hit the singularity in a fraction of a second, but still, it would be at the singularity, not at the horizon. Okay, I don't know, are there any things left to, yeah?
I want to ask you a question about the coordinates.
Yeah.
The coordinates we've been using correspond to a series of rods and clocks
Yes.
that are outside, that are fixed.
That are what?
That are fixed locations outside the black hole.
Yeah.
They're not moving with respect to the black hole. So it's a little bit, whereas the view that we're seeing of the accelerated coordinates is a series of rods and clocks which are undergoing acceleration. So
Relative to what? Relative to what? I know. It's okay. I know. Accelerated relative to what? Yeah, relative to Alice. Okay, now if Alice falls through the horizon of a black hole, believe me, Bob is accelerated relative.
What I'm talking about is the understanding of the coordinates over near the black hole. You're assuming that we have a bunch of points scattered around in a small cube, and there are clocks there, and they're running. Now, when you get inside the black hole,
Right.
you can't do that actually on the surface of the black hole itself.
You can't stand there.
But you could extend that coordinate system across the boundary of the black hole,
Yeah.
and you still get a series of points and clocks. And the clocks are still measuring time, are they not?
Very, very slow. The time relative to Alice then slows down.
There's nothing to prevent you, in this picture over here, from using a set of coordinates and related to real clocks and rods, which look like that. All right? This is Alice's freely falling reference frame.
Kind of like to draw that picture over here on this side.
Okay, it's just a reference frame which freely falls through the horizon of a black hole.
Okay, but the one we're talking about with the T's and R's is one which doesn't freely fall through a black hole.
That's right. That's the one that looks like this.
Yeah, in order to use it.
And it looks like that outside the black hole.
Right.
And
inside the black hole, if we just extend the coordinates, they look like this.
okay.
Right.
So we can imagine a series of rods and frames which actually extend across.
You can imagine, but they'd have to be falling. You cannot imagine anything standing still behind the horizon. Why not?
That seems to be what the variables are predicating.
Anything that's standing still, that means that a fixed R, a fixed little r,
You can't move along one of those coordinates the way you were able to move along
Yeah.
these coordinates because those coordinates are space lines.
that's right. If you tried to make something at a fixed r here, it would be exceeding the speed of light. Something at a fixed r behind the horizon is exceeding the speed of light.
But isn't that what the R refers to in that equation? Something which is exceeding the speed of
Yes.
light?
Right, behind the horizon it's exceeding the speed. Yeah. So no, there can't be rods which are go through here with these rods just standing still statically. They're going.
So it's basically a notional coordinate system that you can't imagine actually constructing.
Well, no.
Well, you can imagine constructing it, but in here, the things that would measure r would be clocks. And the things which would measure, let's see, this was time. The time coordinate becomes a coordinate like that. So behind the horizon, but they're only coordinates. Keep in mind that they're rather arbitrary. We've just drawn some coordinates. Behind the horizon, if you wanted to measure r, you would use clocks. And if you wanted to measure t, you'd use meter sticks. All right? T flows along here. The same coordinate, same mathematical coordinate flows along here. You measure things in here with meter sticks.
Thinking of an Einstein clock with a photon going.
Well, keep in mind, this is not a problem of general relativity. This is a problem of special relativity. This is just ordinary flat space-time, no gravitating objects, except as seen by an observer who is being pulled along at a constant acceleration. The one thing which is not there in that case would be that singularity. The singularity is really the gravitating object. Right. That's the real signal that there's tidal forces, for example.
Can we go back to way back to where the metric comes from? This is very. It was a solution to Einstein's equation.
Yeah.
Starting from some distribution of energy of mass.
Yeah. That's right.
Or well, what distribution of mass does it start from?
Any as long as it's enclosed within here. So right. All right. So we start with Einstein's equations. We make some assumptions. I'll tell you what assumptions. We first start with Einstein's equations. R mu minus 1/2 g mu equals 2 mu. Okay. Now, or with some 4 pi's and 8's and g's and this and that. Now, we're studying a region outside of a place where there is any energy distribution. And that means that we're studying the solutions to this equation, knowing full well that inside here there may be some material, but outside here, sorry, g mu r. Equals 0. Those are Einstein's equations in the absence of any matter. It's exactly the same as Newton. Newton, you would write del squared of the potential equals the energy distribution, the matter distribution, mass distribution. And outside the mass distribution, you would write 0. You know that inside something's happening, but outside there's nothing happening. And so you ask, what are the general solutions of this equation under certain conditions? All right, so I'll tell you what the conditions are. What are the general solutions of this equation which are radially symmetric? In other words, which are only a function of r. Let's start with this one. What is the general solution of the equation del squared phi equals 0, where phi is only a function of r and not a function of theta, phi, and time, for example? Well, there's a general. What is it? I'm sorry. One other restriction. That is a solution. One other restriction. phi goes to 0 far away. Okay, phi goes to 0 far away. You just told me, in fact, what the general solution is. Ax squared plus by, well, quadratic form. No, a linear form. The quadratic form will have constant on the right-hand side. Linear form. But assuming also that it goes to 0 far away. Well, the answer is there are none. There are no solutions of this equation where phi goes to 0 far away. But now supposing you say, what are the solutions to this equation outside a certain sphere, not caring whether you solve the equations on the inside? Okay. Not worrying about whether you solve the equations on the inside, but only caring about whether you solve the equations on the outside, then there are solutions. Only one form of solution. The one form of the solution is that phi is a constant over R. Only mathematical solution. Now, what determines this constant in the real world? What determines the constant is the mass contained within that sphere. So it's mg, the minus sign. The physics tells you that it's a minus sign, and the mg is minus mg. That's the most general solution of the equation of del squared phi equals 0 if you don't care if the equation is solved on the inside. Now, supposing we take this sphere.
I sort of understood this answer. What I was going to then ask was, what happened to the mass inside?
Well, let's continue to follow.
Okay.
Look, we can ask what happens if you take a very small sphere. Well, the answer is exactly the same, except the mass is inside that small sphere someplace. What happens if you go to the limit of a point particle? You go to the limit of a point particle, and the equation is satisfied everywhere except at the point where the point particle is. Where the point particle is, there's a singularity. That's what R is equal to 0. Okay, so and if you like, you can think of the mass as falling in and all accumulating at a point of space. Where is the material that falls into a black hole? It's on here. It falls in here. And ultimately arrives on the singularity. The singularity is also R equals 0. So all the material that fell in is located in some sense at R equals 0, but R equals 0 is now space-like and not time-like. So where is the material? It's here, if you like, you insist. That being R equals 0. Everywhere is outside of here, which means everywhere is out of here. Einstein's equations are solved with the 0 right-hand side. The only place where there's a source is right here. But that's the end of time anyway. That's just the singularity. For Newton, it's also a singularity, but with a very different character. Does that answer the question? As much of an answer.
Sure. Okay, so what prevents us from Newtonian singularities, if you will, is that eventually things repel each other?
What prevents Newtonian singularities?
Yeah, they're made up of atoms, which you can't.
Yeah. Right, that's a fair question.
So is there something is it possible there's something in here that's preventing the singularity in the same way?
There's a very interesting history to this question. It was known, I don't know how far back it was, that a bunch of mass points in Newtonian physics will not collapse to a point. Will not collapse to a singularity. Or let's put it this way. It's a real set of measures, 0 initial conditions, which allows it to collapse to a singularity. And the reason is just the tiniest bit of angular momentum of one particle relative to the other will have them miss each other. Just a little bit of angular momentum will provide enough centrifugal force that they will... So unless they are really very, very symmetrically distributed with no angular momentum at all, they will just go past each other and come and miss each other and not form a singularity. This was known. This was a theorem about classical mechanics. Because of it, Einstein assumed that a black hole could never form. He assumed that somehow the same thing would happen, and it would be impossible.
Is that the same thing that makes globular clusters basically stable as a whole? I mean, they live for a long time.
They do it for a long time.
No.
No. Yeah, that's right. Okay. It's different here. I'll come here in a minute. Just take a single point particle. Suppose there was for a moment a singularity in Newtonian physics, point particle. And then you throw another one in. Unless you happen, it's a point particle. Unless you happen to aim it with infinite precision, it will miss this point and just go back out. What happens here? What happens here? Once a particle passes the horizon, there's no way that it can escape hitting that's because the singularity is a different character. It's the end of time rather than being a point of space. So Einstein was wrong. His logic was wrong. He had a picture that the singularity is a point, and that anything that tries to add some mass to it will miss it and go back out. Whereas the singularity is a real trap. He didn't understand the idea of a horizon, and that the horizon was really a point of no return, and that once you passed it, you were close.
You mean it's not good enough just to have a collapsing star providing a lot of pressure to drive everything inward?
Classically, I mean, Newtonian.
Yeah.
Yeah, no, doesn't happen.
The thing I don't understand is, well, this presupposes that there's a singularity to begin with, doesn't it? Because otherwise, the whole argument you gave that, otherwise...
Electrons are singularities. Yeah.
I mean, it's not clear from this that there exists a singularity, you know what I'm saying, that comes maybe by observation.
I'm saying even if there were a singularity, you couldn't add to it.
Right.
Even if there was. So even if you could get one started and had one, you couldn't add to it. If you can't add to one having one started, obviously you can't make one.
Yeah,
but let's say, in terms of phase space, the picture changed from a classical picture to later on the quantum mechanical picture. And when you look at the incompressibility of phase space, the incompressibility is there because of Planck's constant, which suggests that...
No, the incompressibility is there because of Leonard's theorem, not because of Planck's constant. The incompressibility of phase space is a classical theorem. Right. Keep going, because you're asking me a question, I think.
Right. But then wouldn't the Planck's constant, wouldn't the basic uncertainty relation prevent any further compression, so to speak, in the phase space if you were looking at the black holes in phase space?
So the problem is that in order to have a resistance against compression, you have to have a reasonable density of matter and a reasonable amount of kinetic energy and so forth. And then you can't squeeze it because you can't squeeze it in the phase space. But if you look at how dense something has to be in order for it to form a horizon, the answer is if it's heavy enough, the density of it can be negligible. The kind of forces you're talking about which prevent collapse, it does have to do with the incompressibility of phase space. But just think of the incompressibility of phase space as providing a spatial force which keeps things from collapsing. And you get into trouble, typically, in compressing when pressure gets too big, when density gets too large. How large do you have to make the density to make a black hole? Let's try to estimate it. You have a given amount of matter, rho. Let's say. We'll get this right. Mass is equal to 2 mg over r. Mass. 2mg is equal to r.
There we go. Times c squared.
Right.
C squared.
See?
Isn't there c squared?
Yeah. 2mg over c squared. Okay. Let's divide this by r cubed. Okay. Why? Because I'm interested in m over r cubed, which is density. The bigger the black hole, the more massive the black hole, the smaller the density of a collection of material would have to be before it forms a black hole. Why? Take enough mass, and you put it in a volume, the density only has to be of order, what does this mean? I mean, R is of order is equal to 2mg. 2mg squared. So if you have a given amount of mass, in order to make it form a black hole, the density only has to be 1 over 2mg squared. This is why people are very, very certain that black holes form. They were very certain before there were astronomical observations. You don't have to make it. You have enough mass, arbitrarily low density, let's say it another way. Let's take an arbitrarily low density rho. Rho is as small as you like. Particles every 60 meters, whatever it is. Now take a big enough volume, take enough of them, a big enough radius of them. How much mass? Let's take a radius r. That's the radius r. How much mass is there? Well, rho times r cubed. So 4 pi's and so forth. No, it's 4/3 pi r cubed. No, right. This is order of magnitude, the amount of mass is there, right? This is it. So r, even for this very low density, r, the radius of the ball of mass, is m over rho. And rho is fixed. Rho is just this very low density to the 1/3 power. No matter how small rho is, if you make m big enough, this will be less than twice mg. Why? Because this increases linearly with m, and this only increases as m to the 1/3 power. So for a fixed but tiny rho, you can eventually make m over rho to the 1/3 smaller than the Schwarzschild radius. Once it's smaller than the Schwarzschild radius, it's a black hole. So no matter how rarefied the material is, if you create enough of it,
If you take the vacuum energy at a certain energy density, what would be the associated Schwarzschild radius to create a black hole with that density?
You mean with the known cosmological the radius of the universe?
Is that what it would be?
The radius of the horizon of the universe, yeah.
Really?
Yeah. Yeah. 10 billion light years. So I think we can be pretty sure that in our universe there cannot be a black hole of size bigger than 10 billion light years.
So can we consider ourselves being inside a black hole?
No, not inside a black hole, but inside an inside-out black hole. It's an inside-out black hole, and that it's surrounded by a horizon. But the analog of the inside of the horizon is the outside of the region. We, on the inside of this sphere, are as if we were on the outside of the horizon. And outside the horizon, things fall away from us. They don't fall toward us on a big enough scale. Because of the dark energy, things fall away from us. They don't fall toward us. That's the accelerated expansion of the universe. things fall away from us, and because they fall away from us, eventually, if you go far enough out, you will find them moving faster than the speed of light relative to you, and that becomes a sort of exterior horizon. But it's not like being on the inside of a black hole. Being on the inside of a black hole, you crash into a singularity eventually. Being on the inside of a cosmic horizon, you just stay there forever.
Well, if the singularity is the end of time, how does it ever happen that you do reach it?
The end of time is probably wrong. It's the end of time in the sense that death is the end of time. And you don't reach it.
Just proper time to change that.
Yeah, the proper time to the singularity is fine.
And so wouldn't we have a fixed R at that point? And that's,
What's that?
at the singularity, even though R is 0, you would still have a fixed R, which would put you traveling in theory faster than the speed of light at the singularity.
Say it again.
When R is 0,
Yeah.
at the singularity, then you also have a fixed R, which would...
You can't fix R, because to fix R, you have to exceed the speed of light.
Right.
Yeah.
But you would have a fixed R at R is 0, at the singularity. It would be a fixed R.
Well, as I said, I mean, the physics of what happens when something hits the singularity is obscure at best. There's no sense in which it stops. It just, I don't know what to say about it. Physics doesn't know how to get there. Densities become so large, pressures become so large, tidal forces become so large, that no matter how much physics you know, you will always go beyond that. So if you know physics, temperature will become infinite, pressures will become infinite, densities will become infinite. So if you know and think you understand physics in some desired density, that means that you can understand what happens near the singularity in some shell. But it'll always get worse. If you wait long enough, not very long, it'll get worse. And you'll always be driven beyond what we know about matter. So, is it the problem that we don't know enough to figure out what happens at the singularity? Well, I don't think so. I don't think that's the point. I think nothing survives to find out.
It seems to me as long as you stay outside, it's also irrelevant, but
That's true.
because nothing that goes on the other side can affect.
That's right. That's right. But you could jump in to find out. You could jump in.
So, but
Say,
I
I'm curious.
postulated for steady out.
If you're outside the black hole, you stay outside the black hole, the singularity is irrelevant. If you jump into the black hole to try to find out what happens at the singularity, you're not going to find out either.
Or you can't do it, you can't tell anyone it's on the other side.
You can't know.
It's not only that. It's not only that. Eventually, let's look at it. Let's look at it carefully. Let's take two atoms falling toward the singularity. Here's the singularity. Here's two atoms. Now, atoms can send back and forth messages. Messages can simply be the photons that make up the Coulomb field. But the fact that this atom is influenced by that atom, well, we know atoms influence each other and so forth. But when they get too close to the singularity, this atom over here cannot send a signal to the other one. Why? There's not enough time to send a signal. They fall out of causal contact with each other. They can no longer influence each other. And so, as you get closer and closer to the singularity, the atoms of your body fall out of contact with each other, and you just disintegrate into a collection of uncoupled atoms that have no connection between them. But it's worse than that. The electrons in the atom fall out of contact, out of communication with the nucleus. And protons and neutrons inside the nucleus fall out of contact with each other. So everything just disintegrates into completely uncoupled somethings, bits, which don't talk to each other.
Is that really the
approximation that you made on the metric to make a correspondence to the regular geometry only work where R is near the torsional rates.
Yes.
So by going near the singularity, you're going far from the Schwarzschild radius at some level.
You are.
So,
But I've
so
drawn
that's
the
not
picture.
right.
I've drawn the picture of what that metric really does look like within the horizon also, and that's what you see.
Okay, so there's some other approximations that make it right on the other side.
Yeah.
Yeah. So that's more like a Penrose diagram than a real work.
I'd say crystal diagram.
So, it's not the singularity that the metric pulls up. But
The singularity what?
the Barber time is undefined. But on the other side of it,
On the other side of the singularity?
yeah, on the other side of it, it's a structure, it's a value, right?
The metric is just ill-defined on the other side of it. It's just not defined on the other side of it. Or if it is defined, nobody knows. Well, you simply go through physics, which is totally unknown.
But I was thinking, I mean, the coordinate exists, right? There's a t that's larger than that.
Well, how do you, all right, so if you're a mathematician, you could ask, can you analytically continue the metric past that point? To where? To what? To R, you can.
So just think of the value that's on the other side of it. And then the other question is,
Let's see, can you, R, so we want R to be more, where do we want to continue this to? We want to continue this to where?
R would be negative.
R negative. So what happens if you try to continue this to R negative? This becomes positive. This becomes negative.
it is defined, right? And then is it obvious that I mean, there's no mass actually.
There's no what?
There's no matter that can get past the surface, but is it obvious that light can't go past that surface?
Well,
For example, tape starts on the other side. You start with the line on the one.
look, you could draw light trajectories through there. There, but the light trajectory is likely.
And then you had an observer on that side already. You started on that. Well, I'm just saying, is there any reason that it can't happen?
I know. But we can't find out. Even if we're willing to jump into the black hole, we can't find out.
You mentioned one time, if I heard correctly, that you don't think information is necessarily lost. So
Well, that's quantum mechanics.
what's the argument?
The whole book you wrote. Let's not get into that now. Let's be on my pay grade and see.
Okay, when Alice goes through the horizon and she's carrying a meter stick, does her meter stick suddenly become a clock?
No! No, crazy things Alice. Here's Shirley. Shirley is at one end of the meter stick and Alice is at the other end. Here's the meter stick, here's the meter stick. Nothing happens to it. It just goes straight through. There's nothing fancy happening at the horizon. No, the meter stick does not become a clock. Moreover, Alice's clock does not become a meter stick. This way. It's just using stupid coordinates. Using stupid coordinates which you call R, and you should have called something else when it gets behind the horizon. Just because you call it R doesn't mean you measure it with units.
Actually, there's no difference between a clock and a meter stick. There's really no difference between a clock and a meter stick.
See?
There's no difference between a clock and a meter stick. Because how do we measure time? If you think about how we measure time, you'll end up with that difference.
can use meter sticks to help you measure time. But a meter stick is a meter stick.
Well, that's the point. There's nothing else. There's nothing else that is non-mechanical or physical that defines time. You have
Nothing dramatic happens to Alice and Shirley as they go through. Absolutely not.
Assuming you have Bob or have a reflector, right? And Alice was sending a signal that she got back, right? Is she going to see anything change as she goes over the horizon, or is it going to be the same?
Bob has a reflector.
Right. If she's sending a message, she's receiving a message.
So Bob has a reflector.
But the reflection doesn't get back.
Here's Bob. Now, we do have to keep track of the fact that Bob is accelerating away from Alice, but that's okay. Keep accelerating. Alice is here. Sorry, what is it? Alice?
She's free falling in.
She's still outside.
Yeah, she was
Oh,
outside.
she's outside. She's outside and she sends a light beam. Here's whoops. Here she is. All right? Crashed into the singularity over here. Alice sends a message, and the message comes back. Yep. Alice sends a message from over here, and the message comes back. Behind the horizon. But from here, Alice can no longer send a message. So she can send a message.
So she'll know that something happened. That she crossed the horizon.
All she knows is, well, she knows that she gets crushed in the singularity.
Well, but she wouldn't know that while she's crossing the horizon.
No.
Because
That's right.
she has feeling.
That's right. So what she sees is when she sends a message, the messages take longer and longer to get back. She sends a message from here, it just takes a very, let's forget the singularity. If she sends a message from here, it takes a very, very long time for it to get back. And what's more, it gets back very, very redshifted. So as she gets closer and closer to the horizon and sends out her just usual radio waves, those radio waves have to get to the Bob, which takes a very long time, and then have to come back, which takes the same time, and they have, the moving mirror has redshifted the photons, so the photons get very, very redshifted, and so what Alice would see would be a very, very redshifted version of what she's saying. But she cannot see an image from here. There.
So why is the maximum wavelength the size of the black hole from that analysis? Because it would seem we're just stretch out and down.
No, we need some quantum mechanics for that. Without quantum mechanics, we can't answer that question. Without quantum mechanics, the maximum wavelength.
How is the gravitons can escape a black hole and photons cannot?
Who said that?
They exert gravitational force, black holes do. And we do it by exchanging gravitons?
You're taking too literally the idea that gravitational force comes from gravitons being jolted back and forth. That's or if you like, you can think of the gravitons as being emitted from near the surface of the black hole. You can, it's perfectly okay to imagine that all the material of the black hole accumulates, since it never gets to the horizon, it must accumulate at the horizon. It must keep sinking in closer and closer, asymptotically getting closer and closer, but all of the mass is concentrated in a little thin shell. From the point of view of somebody outside, it's concentrated in a very thin shell near the horizon. If you like to think of gravitons being jumping back and forth, okay, do it. But they're jumping back and forth from the surface just above the horizon. So from outside, just think of the material as collecting in kind of sedimentary layers, which are forever falling closer and closer. This is a classical statement. Which are forever falling closer and closer and thinner sedimentary layers, never quite getting there. But their mass is there. Their mass is there. You can tell the mass is there because you put a surface around there and there's gravitational field coming out of it. And you can always think of it as the mass being localized just in a very, very thin layer.
Very interesting about black black holes which are not spherically symmetric, that might, for example, might be rotating?
Yeah, rotating.
Or so they would be flattened out or something of that sort, extremely flattened out?
There's a limit on how fast they can rotate and how asymmetric they get.
So basically, they can't look a whole lot different from these things here.
That's right.
And
Rotating black holes don't look a whole lot.
And they couldn't have parts to them, like they decide to have parts rotating around each other. But for example, be a binary star that's collapsed and rotates.
A binary black hole.
Yeah, some kind of a binary object that fit inside a black hole. The pieces would collapse under a singularity, and it would stop that.
Yeah. I mean, you know, here we have a couple of binary things going around each other inside a black hole. Okay. That's really not very different than an atom with an electron going around a proton.
And so there's no need, for example, for gravitons to escape the black hole and tell us that that's what's going on inside.
There's no need, and it's not possible.
Right.
Going back to
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.
Blow out the candles! Blow out the candles! I said blow out the damn candles!
Stop it, Frank! You're killing us!
Blow out the candles!